Hi, I'm Curt Frye, and in this movie, I want to start a technical analysis of slot machines with the goal of determining how to design a machine mathematically that is both playable for the player and provides a specific profit for the casino. The sample file I'm using, slotsmovie01, is an Excel file that you can download from the link that is provided in the video description below. The math of a slot machine is based on its payoff table, and that is what I have here in this workbook. We're generating a random number from 1 to 10,000, and actually it's a pseudo-random number because we're using a computer to generate it. And for any result of 1 to 4,500, the player will receive 0 payoff for their bet. So they put 1 coin into the machine, there's a spin, and they receive nothing back. Another 38.5% of the time, they will put 1 coin in and receive a payoff of 1. But it's important to remember that they are not making a profit of 1, they are breaking even on the spin. So the coin goes in, never to be seen again, and the payoff of 1 gives them a different coin back. And the other payoffs are below, and they follow the same logic that I just described. The contribution is the amount that is returned to the player. So you add all of those up, multiplying the probability or percentage by the payoff, and you get the contribution to the player. And at the bottom, when you add all those up, you get a contribution, in this case 0.962, which indicates a 0.038 or 3.8% house advantage. So this is actually a pretty good slot machine by most standards. To the right, I have also calculated the number of hits for each of the results. And to calculate that, I've subtracted the lower number from the higher number. So I go from 4,500 to 8,350, and that has a difference of 3,850. I had to use the n function to avoid an error in cell G2. So in G2, if I type equal A2 minus A1, and A1 is not a number, and press enter, I get a value error. So instead, and I'll press Control-Z to undo, I have a formula that uses the n function. The n function returns a number if the value is a number. Otherwise, it will provide a value of 1 if we have a value of true, or it returns 0. So subtracting 0 from 4,500 leaves 4,500, and of course, because the other values that I'm using are numbers, they are subtracted normally. I can use each of these calculations and the numbers given to derive a new payoff table that will provide a specific house advantage. To do that, I need to set in my starting values. So for a 90% payoff, in other words, a 10% house advantage, I'll start with values of 4,800 and 8,300 in cells A2 and A3. So I'll select J2 and J3 and paste my values into A2 and A3. And again, I want to have a player receive something 52% of the time. So they won't receive anything in return 48% of the time, but the other 52% of the time they will. But also, I set the result of an even money payoff, that is 1 for 1, at 8,300, so 35% of the time they will just receive their bet back. So now let's go into Solver and create a pay table that has a house advantage of 10% or a player contribution of 90%. I'll go to the Data tab on the ribbon and click Solver. So I have the Solver Parameters dialog box. My objective cell is the contribution, and that is E12, so I'll click there. I want to set it to a specific value, so a value of 0.9, which is equivalent to 90%. And I'll do that by changing the cells of A4 through A7. And those will be the payoffs for 2, 3, 4, and 5 coins. So I'll click the Collapse Dialog button next to by changing variable cells. Then I'll select A4 through A7 and click back. Looks good. And now I can add my constraints that will allow Solver to create a model. So I'll click Add, and I'll drag the Add Constraint dialog box down a bit. The first thing I'll do is ensure that the changing cells are all integers. So I will select A4 through A7, And then for the comparison operator, I'll click its down arrow and then click int for integer, then click add. And now let's say that I want the outcomes of 3, 4, or 5 coins to occur at least 1% of the time. 1% of 10,000 is 100, so I will use the hit counts in G5 through G7 to be greater than or equal to 100, and I'll click add. And finally, for now, I want the total percentage to add up to 100%, or 1. So I'll click cell B12, and then I want that value to be exactly equal to 1. And I'll click OK. Before I run the model, I will use the simplex LP engine. That's because this is a linear problem. I don't use any exponents or division, anything like that. If you're not on simplex LP, click the solving method list box's down arrow and select simplex LP. You will get a solution, although it will take some time if you use GRG nonlinear, but simplex LP is the best way to go. Now I'll click solve, and we do get a solution. So I'll click OK. And let me see, I have counts of 102, 100, and 100, and that is my solution. I have a contribution of 0.9, and the total percentage is 100%. So my solution is valid. But now let's play with this a little bit. And let's say I want to find out if there is a way to have a 90% pay back to the player, that is a 10% house advantage, but still have them win something, even if it's just getting their bet back 55% of the time. So I will change 4,800 to 4,500 here so that I have a record of what I'm doing. And then for the result, in cell A2, I'll type 4,500 and enter. Now I will rerun the model. So I'll go to solver and I'll click solve. And I do get a solution, but you can see that there's a couple of problems in the background, and I'll click OK. So I actually have a number that is more than 10,000, and I also have a negative percentage. So minus 30% of the time, or rather minus 3% of the time, the player is receiving a 10 coin payout. And of course, that shouldn't work. So I need to add a new constraint to make sure that all of my hit counts are positive numbers. So I'll go into solver, click add for a new constraint, and the cell references, and I'll drag this down here, will be G2 through G11, and they must all be greater than or equal to 1. So all of the hits must occur at least once, and the 3, 4, and 5 must occur at least 100 times, and that, hopefully, will give me a house advantage of 10%, or payback to the player of 90. So I'll click OK, and then in the solver parameters dialog box, I'll click solve, and I do not get a working solution. So I'll click OK. And the problem, of course, is the 5. I cannot pay back 5 coins at least 100 times and still have a workable solution of 90%. And I played around with the value in cell A3, and what I came up with is that the minimum that you can have cell A3 set to, with everything else remaining the same, is 8,542. So I'll do 8542 and enter, and then rerun the model in solver. So I'll click there, click solve, and I get 8542. I'll click OK, and yep, I have 100s here. All of the hit counts are positive numbers, although you see that they only receive a payoff of 10 one time. So this isn't the best model, but I did want to show you that it does work at 8542. If I change the value in A3 to 8541 and enter, then go to solver and click solve, then I do not get a workable solution. So 8542 is the best you can do if you want to have the player receive something back at least 55% of the time. This is the first of several movies that I will put out on slot machine analysis, and I hope you enjoyed it. If you did, please like it and subscribe to my channel.